Good morning. My name is Richard Reister, and I'm the Program Manager for the Light Water Reactor Sustainability Program. And I'll be covering the next three calls, RC4, 5, and 6. The first topic this morning that I'll cover is RC4, and that's titled Non-Destructive Evaluation of Light Water Reactor Materials under Extended Service. And we also have on the line with me is the technical point of contact, which is Jeremy Busby from Oak Ridge National Laboratory. So first I'll cover an overview of the Light Water Reactor Sustainability Program and then cover some details of the call. So the vision of the Light Water Reactor Sustainability Program is to enable the existing nuclear power plants to safely provide clean and affordable electricity for extended operation, which we look at as mostly beyond 60 years. And that includes both the fundamental scientific technical basis for the long-term operation as well as the economic basis. The program is coordinated with industry through the Electric Power Research Institute primarily, but also with the Nuclear Regulatory Commission and other industry representatives. And we also have cost share with industry, and we have some pilot plant projects as well at nuclear power plants. We've divided the program up into four what we call pathways, and I'll cover them briefly and then go into more detail on the materials pathway, which is the subject of this call. So in the materials pathway, we try to develop the underlying science so that ultimately we can be able to predict, mitigate, or prevent long-term degradation. We also want to be able to assess performance of essential systems, structures, and components. Materials research includes work on radiation-assisted stress corrosion cracking of core internals. Well, actually, I'll cover that more later. The risk-informed safety margin characterization pathway is to develop tools for industry that will allow them to better understand the impacts of replacement and repair decisions on safety and reliability that will ultimately influence decisions related to long-term operation. The third pathway is advanced instrumentation, information, and control systems, and this is to address the long-term aging and obsolescence of the existing I&C system technologies, and to develop and test new technologies to allow plants to modernize. And this really affects the economics of plants. And finally, the fourth pathway is kind of a catch-all for emerging issues. Right now we're addressing two emerging issues. One is the backfit of cooling towers at existing, the potential backfit of cooling towers due to environmental concerns, and then also we're addressing the Fukushima lessons learned. So some more details on the materials aging and degradation pathway. So we're conducting research to determine how these materials behave in the unique reactor environments. These are high temperatures, high pressure, unique chemistry conditions, neutron or radiation, for example. The slide shows the different materials of interest. We have the first one, the reactor metals, which is the typical thing most people think about. And examples of that are mechanisms of irradiation-assisted stress corrosion cracking, high fluence effects on reactor pressure vessel steels, and crack initiation of nickel alloys. But in addition to the metals, we have materials of concern for long-term plant operation. These include concrete as it degrades, cables, which mostly involve the cable insulating jackets. And we're also looking at the mitigation, repair, and replacement technologies, so weld repair techniques, post-irradiation annealing, and advanced alloys. I'd also mention that we do pilot plant projects where we have looked at materials taken from either operating plants, for example, reactor pressure vessel, Sharpie test specimens, or reactor internal bolts, for example. But also we're harvesting materials from shutdown plants. For example, we plan to harvest some reactor pressure vessel specimens from the Zion plant. So getting to the specific call, it relates to the non-destructive evaluation tools are an integral part of assuring material performance over the extended operations. So material and components under extended service conditions will see very long lifetimes under stress, temperature, chemistry, and neutron and gamma fields. So there's numerous degradation modes that must be considered, and so non-destructive evaluation tools are an essential part of assuring material performance over these extended periods. And so we have an effort to develop new NDE tools, and so the idea of this call is to be able to accelerate this development using modeling and simulation tools to study and optimize the interactions of detecting signals and material microstructures. The development of the new NDE techniques relies on knowledge of the impact of material state on detection signals. So the key is to be able to model how the detection signal interacts with the materials that are being examined. So we seek proposals for advanced modeling and simulation of interaction of non-destructive evaluation techniques with aged materials, with a focus on the development and validation of these tools that model the interaction of NDE signals with aged material microstructures. Detection signals of interest include, but are not limited to, acoustic, ultrasonic, and X-rays are examples. Materials, the focus is on materials that are used in water reactor applications because the program is focused on the existing plants. So these are water reactor plants. Stainless steels, low alloy steels, nickel-based alloys, concrete, and cable insulation are examples of the materials in conditions relevant to extended service, such as irradiated microstructures, oxide layers, fatigue damage, and others. Universities should be expected to produce concepts, supporting data, and other model predictions demonstrating the viability of these techniques with a high level of quality assurance. And that's the end of my presentation. Let me see if Jeremy Busby's on the line, and we'll see if he has anything he'd like to add to the discussion before he takes some questions.
I'm here, and I think that covered it very well, Rich. Thank you.
Jeremy, are you there?
Yep, I'm here. Rich, I don't have anything to add. I think you covered all of the key points and the interest and motivation for this, so I'm ready for questions. Thanks, Rich.
All right, so see if we have any questions.
We don't have any questions right now, but we'll. Oh, here comes one. Is a straight material study of interest, i.e., radiation damage to concrete, or must NDT be also employed?
This call is focused on the NDE and modeling simulation. Past calls, the last 2 years, have focused on the materials degradation issues, and I think there's even an award on irradiated concrete the year before last. So we are really trying to focus on the non-destructive evaluation and testing aspect of it this year.
Will the high temperature NDE techniques be of interest?
High temperature meaning light water reactor relevant conditions, yes. High temperature for gas reactors are probably not as relevant for this program.
Is HBS of interest?
I'll be honest, I'm not sure I understand the HVS acronym.
I don't either.
We'll wait for a response back.
Okay.
For RC4 NDE evaluation, is modeling the only thing that you are looking for?
No, I think modeling is an important part of that, and modeling is proposed as a tool to help optimize the development of the sensors and understanding the interaction of sensor signal and material performance. Experimental and sensor development can be elements as well.
HBS stands for high burn-up structure.
Well, HBS, so that would be so a fuel structure. Those aren't as relevant to the materials pathway, which is focused primarily on the long-standing and safety-related structures such as vessels, internals, concrete, or cable and cable insulation. We do not have any active work related to fuel assemblies or fuel components.
One last question.
Okay.
Is a major focus on microscale modeling and simulation mandatory?
I would not say major focus or even micro scale. A number of the radiation,
Jeremy, you're still
I'm sorry, material degradation phenomena can be larger scale. For instance, the formation of voids in large concrete structures. The understanding and development of a tool to look at large grain structures in cast stainless steel piping or components. Those would not require micro or lower scale evaluation or simulation of material processes.